So I think so what Jay talked about more what is happening kind of I would say at the silicon level, what is happening in the storage pieces of it. I'll take it from here and more talk about at the infrastructure level, what we are seeing, what we are working on, what are some of the trends that when it comes to infrastructure, is it more, what should we be thinking at the node level? What should we be thinking about at the data center level? So from an agenda, I'll just talk a little bit about what we have been doing in this particular space. So before that, about me. I work at Dell. I've been there for about 20 years. I've been doing a lot of signal integrity work and then moved into the AI space, working in GPUs. Right about, I would say, around 2014 is when I picked it up and started working on it. At the end, I am an ultra runner. That comes first. Everything else is a secondary to me. So if you live in Austin, I'm always in the trails out there by myself, actually. So, okay, compute for AI. This is a question that always comes up. What is the compute for AI? I see it as a very wide scope for it, right? When it comes from a silicon point of view, where CPUs, where CPUs can be used to where GPUs, FPGAs, and domain-specific accelerators are coming in. Each one has a role to play, I would say. CPUs, they are kind of your traditional workhorse, I look at it. They're very good also with a lot of the instruction sets being built in. They've been pretty good for doing a lot of inferencing. CPUs with a large memory set associated with it can do a lot of large image processing. That's where CPUs come in play. Of course, CPUs don't have what I would say the very fast computation capabilities that you bring with a GPU. GPU with their architecture, they started off in the graphics. Now with added tensor cores, they've been being picked up, I would say, in a lot of the AI use cases. FPGAs with their pipeline instruction set, they're good for speech to text. And then the last category, DSAs. Domain-specific accelerators to me is everything that is very focused on just doing pure matrix multiply. That's the primary goal for DSAs. And DSAs they're going to be specialized. They're going to be specialized for a workload. You cannot take a DSA and try to use it for some other IT-based workloads. It comes down to what is the processing power? What is the when you do the programmability piece of it? You look at CPUs. CPUs are versatile from that point of view. GPUs over time, with the CUDA has a lot of decades of work being done over there. So GPUs you get the higher performance. There is the programmability aspect of it. FPGAs are more targeted. And then when you look at DSAs, DSAs are very from a software development point of view, they are very narrowly focused because you have to think about that. Since they're very focused, I would say, on matrix multiply and a specific workload, the software has to be tuned for it. The y-axis gives you what you get from a performance per watt. Performance per watt will be, of course, better and higher when you look at DSAs versus when you look at where CPUs are. That's how this processing landscape is evolving. DSAs, outside, if you look at where CPUs and GPUs have taken off in the AI space, you see also DSAs taking off. You see companies like Cerebras and others coming in. Cerebras, Sambonova, Grok. There are quite a few of them who have shown up and targeting these very AI-specific workloads. The trends that we are seeing from when it comes to AI infrastructure and what is happening in this particular space, there are a lot of form factors out there, be it from the M.2 to the PCIe CAM to the very custom silicon, be it in kind of a very large monolithic wafer scale to what Cerebras worked on, to what we are seeing in now the cache coherent type of CPU, GPU showing up, what NVIDIA came up with the Grace Hopper. But it's getting targeted based on what that workload is going to be it like for training or for inferencing. Inferencing, we are mostly seeing kind of the M.2 embedded form factors, PCIe chem being used over there. And then when you start looking at training, it's going to be more in using PCIe chem GPUs, but then becoming a little bit more custom. So that's what we are seeing from a form factor perspective. That is one of the trends. The second trend is all on this LLM model. Jay talked about how the model size is increasing. What we are looking at is more what you're seeing just now is a lot of the text-based, I would say, models in this NLP space or in the LLM space. But then you see vision, because there is a combination of going to happen with what do you think about the different sets of kind of data sets coming in, be it for now it's text, but there's vision piece of it coming in, the video piece of it coming in. How do LLMs get used for that? So that's where kind of Andrew put out this particular chart last year in one of his talks, and he talked about how vision models are going to be becoming more dominant and what should be happening from a compute point of view. Large language models, kind of most of you might have come across this, where how LLM model the size and growth. But then if you look on the right-hand side, it's more about the compute demand. Kind of the compute demand, it's like on a trajectory as these model sizes are increasing. It's on a kind of a 10x trajectory. Even this number kind of that we are seeing is the compute is not enough to solve a lot of the problem, because the biggest KPI when it comes to a lot of the training jobs, it comes down to time to train. How fast can you train? That is going to be the key, and that's what everybody is focused on. That leads into the different type of accelerators coming in. This was a survey done in one of the papers by some of the folks out of MIT. And what they looked at is all the kind of what is happening from the very low power category to the higher power category. You'll notice that there are a lot of accelerators in this space. A lot of them have disappeared over time, but there are still a lot of them trying to target the different spaces that they need to go solve from an AI point of view. There are different math precisions. Every year or kind of every next gen of silicon, you'll notice that the precision keeps on improving or changing, and it's to do with how fast can you solve a problem. That's what we are seeing. So that is kind of one of the impacts. So it's kind of looking at what is happening from the LLM model size growth, form factor, all the different accelerators showing up, and then there's power trend. Now, power is kind of not kind of stopping at some particular point. That power is just linearly increasing. So this plot shows you what we are seeing currently shipping. Like if you look at the highest powered kind of per GPU, it's about 700 watt. And if you look at PCIe chem, they're sitting at about 400 watt. But then if you start extrapolating and you start looking at what is going to happen in N+2, N+4 in terms of years, you can see a trajectory from a power perspective. That puts a lot of pressure on what you should be thinking about from a cooling, because cooling becomes very important. There is going to be a balance between, I would say, air and liquid. It's not going to be kind of you need to liquid is not going to solve everything, because you'll still see a lot of data centers want to pick up air-cooled type of platforms and want to deploy that infrastructure. So that's one of the other trends we are seeing. And then the other one that we are also, because what is happening from an AI perspective is benchmarking is becoming pretty important. How do you standardize? How do you figure out, with all these accelerators coming into the market, how do you figure out that this accelerator is right for a particular type of an, say, a model that you're trying to run? ML Commons, ML Commons started multiple years back. It was an effort born out of what initially kind of Baidu and others came up with different gem-based benchmarks. It then folded into this ML Perf. ML Perf eventually became ML Commons. And if you now look at ML Commons has expanded beyond kind of AI, targeting, training, inferencing, moving into storage, HPC space, and creating different benchmarks. When it comes to all the kind of the models, you'll notice that there is a segment, there are the computer vision class models that they're looking at. They're looking at also in the LLM class, and that's in the bottom where you see GPT-J, Stable Diffusion, Llama. Now, of course, with any benchmarks, benchmarks will always be a little bit in a cadence behind to where the industry is moving, because the growth of LLMs is so fast. You have models almost on a weekly basis getting released from a lot of the top research institutions, from the hyperscalers out there. So it's very tough for even benchmarks to keep up with the latest model. But it is an attempt. It gives you a way, I would say, ML Commons and ML Perf for both training and inferencing, and even what they're developing in the storage side of it. It gives you a way to figure out, can I use this particular accelerator? How does it compare from a silicon point of view? And what is it giving to me in terms of the KPIs that I'm interested? KPIs could be, I'm interested more in latency bound type of applications, or my applications are just more throughput bound, and I'm more interested in that. That's where kind of ML Commons would give you a way to look at it. The inferencing, we've been looking at both the data center and edge side of it. So edge would be maybe near edge to far edge, and the different class of models. And how do you kind of start figuring out what are the durations, or what are the KPIs that I'm really interested in? That is what ML Commons is trying to look at. When it comes to training, it's the same. Like if you look at what ML Commons is doing for both training and inferencing, it's the same categorization from a model perspective and in the benchmarks that are coming out. It is targeting vision, language, and then the last, what you see, kind of the recommender models like DLRM class of model. From a trend now, what we are seeing is what is happening at the node level, that is the accelerators coming in with their, the different power, the different benchmarks that are showing up, the different form factors that are coming in, the different precision of these accelerators. That is putting a lot of focus on where rack power is trending to. And if we look at where rack power is trending to, kind of a lot of data centers before kind of ChatGPT came on, and if you talk to a lot of data center providers, they were about 10 to 20 kilowatt per rack. And that was good enough to run a lot of the IT workloads. But with this growth of LLM, what happened is 20 kilowatt is no longer going to be sufficient. And that, what we are seeing kind of from an AI perspective, is going to go linearly up, like 75 to 100 kilowatt, plus. That could be the rise where, you have a lot of the greenfield type of data centers showing up. It's not just going to, you cannot take a brownfield kind of a data center, go retrofit it. It is going to be, pretty challenging to do it. Some might be able to do it, but it's going to be more the greenfield type of data centers that are coming in and trying to address this particular space when it comes to AI. And that leads to this kind of from what we are seeing at a data center level. From a data center, if you look from, like this is a plot giving you what is the PUE to kind of how we are seeing it from a x-axis, the years have been rolling by from 1995 when we were looking at towers to 1U and 2U to when you move to blades, and now with the rise of accelerators. Kind of each category, you'll notice that the data centers are getting challenged with each of these technology kind of, I would say, cadence or jumps coming in. And when it came to this last around in this the time frame was starting to change around in, I would say, 2018 to 2020 is when you started seeing that, accelerators needed to get up in their power in order to get that performance. So since power was increasing, now you had to start thinking about what needs to happen at the node level. If you start thinking about node level, then you have to think about what is happening at the rack level. If you think about a rack level, then you're now thinking about what should be done at the data center level. It is becoming difficult to cool. Liquid cooling is kind of getting adopted very fast. A lot of the AI, now what we look at it from AI data center point of view, it's going to be more, I would say, hybrid. That is a combination of air and liquid, but liquid cooling is going to be more play a dominant, I would say, role as we move forward in this AI compute point of view. So all those kind of looking at what I've talked about so far, this is a combination of all kind of the factors that are affecting all our infrastructure decisions, right? What we are seeing, accelerator form factors, cooling trends that we are seeing both from air and liquid perspective, what is happening either at the node level, at the rack level, at the data center level, power trends, model size and applications, node power density, all the different data center requirements that are coming in. With all these different combination of form factors showing up, now it comes to, okay, what should we be kind of doing? So where is this AI infrastructure in our head, kind of where is this trending? So the factors which we have already talked about, the accelerator, the power, the size, the cooling, the model sizes and everything, what we think is where this AI infrastructure is trending is no longer when solving for AI, it's not just going to be about I'm going to deploy a single node with 2 to 8 GPUs and try to do my work. We think it's going to be more moving to a cluster level deployment. That's where AI is going, and that's the direction it is heading to. Because it is moving more to a cluster level kind of a deployment, what we are seeing is there are a couple of vectors that are coming in and becoming pretty important. You have to start thinking about what is your fabric design and how are you going to do that networking, because at the end of the day, GPUs or FPGAs or domain-specific accelerators, they are very powerful. We look at it that it's a very big giant calculator, and that calculator can only work as fast as you can feed the data into it. So if you cannot shuttle data into that compute, then that calculator is pretty useless, right? So in order to make that calculator work very efficiently, in this case, all these different accelerators, you have to start thinking about what is your fabric design going to be? How are you going to attach your storage? Where is your data going to be? How fast can you bring that data into that compute element and go solve your problem? That is the kind of the other key. Because of this power and the power per rack that we are seeing and where the trend is moving from an AI point of view, I think so whatever, let's say if today we say we should be by 2025 deploying or thinking about a data center with 70 to 100 kilowatt per rack, I might be at least 20 to 30% off. That's what we are seeing, is that you have to start thinking about a budget from a power at the rack level and a power at the data center level to be, really thinking about what would happen in the next 5 years with all the growth that we are seeing in this particular space. The other kind of what we see is, for all these deployment of the kind of the Gen AI applications, besides what I talked about, like not a single node, it is going from 64 to 1000x type of GPU deployments. That is what we are seeing, and that is putting kind of a lot of focus on the data center piece of it. It's no longer kind of designing a node or an infrastructure and then figure out how will I deploy it. It's more going to be go talk to the data center folks, look at what are they doing, and then build it from there. So it is more kind of a top-down approach instead of just building something with GPUs, put it together into a node, and then say, okay, I'm going to solve your Gen AI problem. I don't think so we can do it. You have to start thinking about where are the data centers? Are you talking to all the data center folks, all the colo folks? Are you talking to them, hey, these are the trends I'm seeing. Can you now start plumbing in that power, the cooling, and everything, and then go build the node based on that one? That is what kind of from a trend perspective we are seeing. So hopefully kind of it gives you kind of a little bit of an idea of what from an AI compute trend perspective, what we are seeing in the accelerator space, what we are seeing at the infrastructure level, and then what we are seeing at the data center level. Open to any questions.
Hi, if all those trends and specialization, do you see a specific design for different AI stages, like inference training? Because today, it's just one size fits all. At least on networking and storage, I see just, there's no specialization, just whatever you design, it's there. Do you see that stratification across different stages on AI?
Yeah. So if it comes, what we are seeing both from inferencing and training point of view, it's more the sizing that you have to start thinking about. And the sizing can be based on a conversation as to, is it more TCO derived? Is that where the interest is? Or what are the different KPIs you're trying to achieve? If your KPI is, so let's take an example for inferencing. If I look at inferencing, if the KPI is I am purely latency bound and I want to deploy an inference-based server in a retail location where I am trying to do these transactions and my latency is, say, in milliseconds, that inferencing solution will be completely different than I will design something for your KPI is in seconds. Then if it comes to throughput, it will be a complete different scenario. The networking, let's say for the near edge to maybe far edge, might be a lower kind of a speed and feed type of application versus when you start moving to the data center. When it comes to very large inferencing, it might be almost the same compute as what you're going to use for training. But when it comes to training, then it comes to what is my cluster? How am I going to do it? The key points that we are seeing, or what I see is at least, is not just the compute, but how is that network attached and how are you going to do all your example checkpoint writing, saving, and everything when you're training. It's because you have to then start figuring out the failure at the node level. If a node fails, what do I do? How are my checkpoints getting saved? How am I going to recover, get my training job back on? That is what I see as a trend.
Yeah, but there is a big difference between like a hyperscaler and just a regular company that wants to do some AI ML and they won't have that stretch, right? So
Correct.
they will need to.
So for
figure out
there,
that.
what we are seeing is more a kind of from a compute, it's going to be looking at, say, PCIe Chem class type of GPUs to more the, I would say, the custom SXM, OAM class based nodes. PCIe type of GPUs, they become pretty important in that category. It's because you can run individual users or you can run individual VMs on it, and they might be just very good enough, like if they're a little bit higher powered in the 300 to 600 watt category, might be pretty good enough to do that particular training run or an inference job.
Yeah, because we see that with particularly with storage, there is no differentiation. It's just people just use the storage as is. Thank you.
Yeah.
So when you say the fabric is becoming the core when designing it, are you seeing multiple layers of the fabric for intra-rack, inter-rack, inter-AZ, cross-AZ, cross data center?
Yeah.
Are those being thought of as one universal fabric that has kind of multifaceted operation, or are those being thought of as discrete fabrics that need interoperability between them?
What we initially, I would say it started off more as discrete, where each layer was really not mindful about the other layer attached to it. But what has happened very quickly with all the LLM training and inferencing, that it's become very important of what your intra, and within that intra, how your PCIe fabric is working to the next layer of fabric be your peer-to-peer GPU link, how you synchronize it over there, to how that is synchronized with the next layer where you're doing scale out. That's quickly kind of happened, and then you see now different efforts in the industry trying to figure out how do you make it talk to at a certain level. But what I think is also going to happen is there's going to be a certain scale that you're going to have as to how many example GPUs you can put together and coherently make them talk to each other in a single domain. And at some point, then you have to move to some sort of a larger fabric, like a scale-out fabric like IB or Ethernet. But how well can you do that communication is going to be the key.
Okay. And so interoperability to this point has been kind of relegated to figuring out right now there's a hard problem of how do you strap all these GPUs together.
Correct.
But once that problem seems mostly under control, then the next problem set after that is, now I have multiple sets of these GPUs strapped together. How do we get those to talk to each other? How do we get
them? I look at it basically scale up to scale out. If you can make that work very efficiently, then I think so you can grow cluster size up to whatever level you want, and you can start training a model. That's where the key is going to be. And it is a combination, I feel, is going to be more of all the different communication libraries to how that fabric library is to what is happening from even the framework level. So there are multiple players coming into that picture.
So economically, training is the only application in the world that's flop bound that we can find. I mean, we're nowhere close to flop bound. Inference is memory bound. It's GMV for the most part. Inference has to become ubiquitous because somebody has to pay for all this crap. I mean, honestly, right? Somebody's going to have to start charging the population to fill the $1 trillion buckets, because they can't do that. Google's not going to pay for this forever. Microsoft is not going to pay for this forever. They're going to charge us for something. Clippies, something. They're going to charge us for it, right? By selling us stuff or whatever the hell it is. And so inference has to become so ubiquitous. isn't the price of inference going to have to be driven to near zero? I mean, aren't you going to have to not worry about the cost of it to get everybody to pay for the enormous cost of doing all this stuff? And is that not going to end? But training will likely never be that way because it's so specialized. If you buy a machine for training, you can't use it for anything else very well. You can use it, but you can't use it very well. Are we going to be driven to a completely different machine for inference versus, I mean, right now we're not because we're in infancy, but aren't people going to realize, shit, I'm paying $40,000 for a GPU and all my inference could run on a thing that costs $19 with a lot of memory bandwidth? And are we going to see memory bandwidth cost to low capability processors, the cost of that be driven to zero? Is memory bandwidth going to be free? It almost has to be, doesn't it? I mean, to make it as ubiquitous as we're talking about, having to have it to pay for all of it. So it seems like, yeah, for right now we've got these growing pains, and yes, pod to pod is bespoke. We have that at the lab now, but it sure seems like for us, inference is likely to be a whole different, appliance or something you buy that's just way numbers of simple cores that have massive memory bandwidth so they can, predict the next word or whatever it is they're doing.
Yep.
I don't know. Am I wrong?
I agree with a lot of the points you brought up. Do see it that way, but where I see, at least my viewpoint on the inferencing piece of it, there is going to be, like I would say, the hyperscalers who are doing inferencing and the GPU cloud providers who have shown up and doing LLM serving. They might have a different TCO in mind because they can still charge and get monetization out of it. But there will be this class, what you're talking about, where how can you make that inferencing very cheap or you're not paying for it? That's where kind of I really see, CPUs, everybody still needs to use CPUs in some shape and form, right? So how do we figure out that those CPUs become in a point where it is almost free? Like I can use that CPU for something else, even my IT workload. But you are absolutely right. Like, kind of that's where we see. Because at some point we have to do the monetization piece of it. If that monetization doesn't come up, then all those charts that we have for our LLM growth and model sizes, everything, will disappear.
All right. I know there's another couple questions out there, but in the interest of time, we'll go ahead and move on.
Yeah.
Bhavesh, thank you very much. Definitely feel free to get with Bhavesh later.